In this paper, we present a zero-shot registration pipeline called Buffer X, which is trained on a single dataset such as 3D Match or Kitty, and performs well on any test scene without any prior knowledge or user parameter tuning. To achieve this, we first thoroughly analyze and identify three major factors that are crucial for achieving generalization in point cloud registration. The first issue is that most registration methods require manually tuning the voxel down sampling size and search radius for each new dataset. This reliance on user-defined parameters hampers generalization because performance degrades if these parameters aren't optimal for a different environment. Second, learning-based key point detectors are often brittle when faced with new domains. A key point network that works well on its training data may pick unstable or non-repeatable points in unseen scenes, undermining the registration accuracy on out-of-domain data. Third, feeding raw coordinates into the network makes models sensitive to scale differences. Without normalization, this might lead to in-domain bias and poor performance on unseen datasets. To address these three key issues, we introduce Buffer X, a zero-shot registration pipeline that performs well on unseen datasets. Specifically, first, Buffer X automatically determines voxel sizes and search radii using geometric bootstrapping. It analyzes point cloud distribution and density, tuning parameters on the fly for adaptation without manual adjustments. Next, instead of relying on learned key point detectors, Buffer X just uses farthest point sampling to select key points. Farthest point sampling outputs a robust, evenly distributed set of key points across the source and target clouds. Third, Buffer X normalizes each key point's local patch to a fixed range of -1 to 1 before feature extraction with mini-SpinNet. This removes scale discrepancies, enabling descriptors to capture geometric shape rather than absolute size. Furthermore, our pipeline extracts multi-scale descriptors from local, mid-level, and global patches. This captures distinctive features robust to density and scale variations, improving correspondence accuracy. Finally, Buffer X performs intra-scale matching to find initial correspondences within each scale, followed by cross-scale consensus maximization to refine correspondences for more accurate pose estimation. We evaluated Buffer X on a challenging generalization benchmark of 11 diverse indoor and outdoor datasets. Trained only on a single dataset, our method achieves high registration success rates across all these unseen datasets. Qualitative results also illustrate that our Buffer X successfully aligns the source and target point clouds, supporting our claim that Buffer X can handle different environments and scales while still achieving precise point cloud alignment without any prior tuning. In addition, we conducted ablation studies to validate each module, confirming that each component plays a crucial role in enhancing generalization and registration performance, ultimately contributing to the robust results of our Buffer X. In summary, Buffer X is a zero-shot point cloud registration pipeline designed for strong domain generalization across varied environments. We also introduce a comprehensive generalizability benchmark and demonstrate that Buffer X sets a new standard for reliable 3D point cloud registration without test time tuning on unseen datasets. Thank you for your attention. Please refer to our paper for more details and additional results.